this is the scenario of heterocyclic chemistry towards students, as if it is going to kill us. But in reality, the this chemistry is as beautiful as this kind of pictures. Just this is for fun purpose, so don't just take any things. So basically, that's the real scenario, heterocyclic chemistry. Then let us understand why I am telling that much beautiful. Let's say we have a benzene. We're trying to construct one heterocycle with this benzene. Then what you will say? TH. Then okay, say you will say okay, sir. So basically, we looked at here. Let us try we are replacing something here, but we will have full this kind of systems. You will say, sir, okay, we need this kind of architecture here. See, so this architecture you now mimic this CC bond and CH bond. So 3 sigma architecture here. Then what do we say? We need one p orbitals here, vacant p orbitals. If this is vacant p orbitals, then it will bypass the electron delocalizations. So 1 plus 1 vacant p orbitals. Vacant p orbitals. This is your demand. Then what will you do? Now you know a lot of chemistry, you know. So which atom you choose? Let's say you have choose your nitrogen, because you know that nitrogen can have 3 sigma bond and 3 sigma orbitals on p orbitals. This is the nitrogen hybrid orbitals. So this is, let's say, its bonds formed from sp2 orbitals, this from sp2 orbitals, and this is also one sp2 orbitals. Then what we'll have? As this is sp2 hybridizations, then we will have a pi bond. Basically, this is the pi orbitals. Now, here we have 2 lone pair here, as we need vacant p orbitals. Now, you move it to your own way, own directions. Basically, now you think. So now you adjust these things here. If you put this nitrogen here, then what will happen? This nitrogen here, now it has a p orbitals. That p orbitals will take part with delocalizations. It's okay. It have 2 same bond connectivity like benzene, and instead of benzene, but we have 2 lone pair in sp2. That's the real secret behind point atom mutation. So here, what basically we are doing, we are replacing one CH moiety by N. Basically, we are replacing one CH moiety by N, not N. Really, sp2 hybridized nitrogen. Again, sp2 hybridized nitrogen where the lone pair lie on sp2 orbitals. That's the complete definitions. Where the lone pair of electrons lie or resides in sp2 orbitals, because your p orbitals, vacant p orbitals, means your p orbitals has to be vacant, otherwise it cannot take part delocalizations with these 6 ring electrons. That's the beauty of this replacing or replacement of hydrogen. Normally, if we see pyridine, if we say so nothing comparable, we can see changes with benzene, but this is the difference. There is a totally logical replacement. So in the language of biology, you can say basically it's a mutations, it's a point atom mutation. Basically, what you are doing, you are mutating, like biological concept, you are mutating, or CH moiety is mutated by N atom. Basically, telling N atom is a wrong term, because N atom where this N is sp2 hybridized. Not only that, where the lone pair lie on this sp2 hybrid orbital. This is the complete scenario. Now you understand just after the immediate first class why I described that this chemistry is as much as beautiful like that picture. And slowly you enjoy all the chemistry here in that way. As if someone is telling you a story and you are enjoying that things. Basically, here the chemistry is very much simple as well as interesting. Now you are brilliant enough, you learn that CH moiety can be replaced by nitrogen. You logically explain that, you logically understood that. So if you replace another CH moiety, by nitrogen, you can replace, then what will happen? Nitrogen here was already replaced, now one more nitrogen here. So this is different heterocyclic compound. Its name is, we should not be bothered about the name, but yet I am writing pyridazine. Okay, now understands it. Okay, then ask. So you have replaced this, and you are telling is it as aromatic as that of benzene. So what is the minor change? So in the previous classes, one of not previous classes. In somewhere in your BSc, you have read about spectroscopy. Here, by spectroscopy, we try to understand what change happened here. Basically, look, we have a hydrogen, means three types of hydrogen. This hydrogen is at ortho with respect to this nitrogen. I shouldn't say ortho. These are 2 position, 3 position, 4 position. So this hydrogen is closest to the nitrogen. That's why as nitrogen is electron withdrawing or electronegative atom, I shouldn't say electron withdrawing, electronegative atom, then its electron deficiency means it will be electron deficient. It will have electron deficient environment. So this hydrogen has electron deficient environment. Deficient environment. So for this, delta H will be at higher ppm values. So the value is 8.5 ppm. And for this, look at the value. Here, the delta is 7.1. And here, delta is equal to 7.5. You will say, why sir you are writing the 7.1, 7.5? I can understand 8.5 is okay. It's closer to nitrogen, nitrogen electronegatives. So this nitrogen has electron deficient environment. Then with respect to this hydrogen, this hydrogen is closer to nitrogen. With respect to this one, this is 1, 2, 3, 4 carbon array. Then we could expect the value should be reversed. But why it is like that? The reason is that basically this nitrogen, if this kind of delocalization happens, see what is going to be. This is N minus here, because this type of electron delocalizations, this carbon has quite positive charge. That's why this proton is quite electron deficient. That's why its delta is quite positive. And here, when you are delocalizing, you see this is always this carbon within to some extent with electron rich environment. That's why delta H value for this hydrogen is equal to 7.1. That is the lowest. That also one fantastic thing we can discuss. Okay, so we are happy with that. And now someone is asking, so sir, you told about the mutation of or replacement of one CH group. Then if I want to replace this group by something, then what is going to there, what we are leaving there? See, this system is here. These systems, because we are cutting this system out, this system. So if we replace some atom here, then we will have these things. Then with logic, how we can do that? Again, so here we are cutting with two electrons. Then we have to provide two more electrons. That is a pi electrons. So two more pi electrons, or not pi electrons, two more electrons in p orbital is required. If we have a p orbitals here, means let's say we have p orbitals here, and that has two electrons. It means it's equivalent, as if these two electrons is equivalent of these pi bonds. That's why we need two more electrons in what? Pure p orbitals. Then again, your nitrogen is a good friend. What will do for nitrogen? If let's say have a nitrogen, it will be sp2 hybridized, and this is the pure p orbitals. Here we have two electrons. So basically, see, here we will have NH, and this will be for CC bond formation, for NC bond formation. See, you take this skeleton, put it here. So basically, what we are doing, we are getting a pyrrole, NH. That's the concept. So if I summarize, what we can do, what we can do that if we replace, let's come here. So if we replace one CH, one CH by nitrogen, which type of nitrogen? Nitrogen with sp2 orbitals with two lone pair electron in sp2 and vacant p orbitals. Then we'll get these things. So if we want to replace one CH bonds, we have to use these things. So it is pyridine. And if we want to replace these things, we are going to do the job again by nitrogen, where this is a fantastic guy. Here we need two electrons here. That's the fundamental difference. So this will used for the formation of NC bond. NC bond, this will be NH bond. Then we will have these things, a pyrrole, two lone pair. Okay. So that's because of lack of time. Just for the basic things, I have to stop it here. Just to believe me, the replacement logic is that much beautiful. Okay. Now, because so wait a bit, just I'm waiting because I have to attend one call. Maybe I will come back within 2 or 3 minutes. But please wait. Okay, thank you for waiting. I hope you are in line also. Let's check it. I will keep. Yeah. Okay. Then basically it's a nitrogen. So you will ask now, you are very clever one. Normally these things we tell as imine. Imine. So imine is very unreactive, reactive. This is reactive. Then you can ask, sir, so this is basically imine. So then it imine, but the molecule is aromatic because of this fantastic replacement strategy, or the molecule is aromatic. So this is basically now I am write down one fantastic statement. Pyridine is an unreactive imine. It's a statement they have quoted from the book of Claydon. So if you find some time, read this book. It is more interestingly elaborated there. Just because of our shorter time, we have to discuss that much. Okay. Pyridine has one property. Pyridine can act as nucleophilic catalysis. Nucleophilic catalysis. How? Let's say we know that because of this lone pair, pyridine is nucleophilic in nature. So we have this kind of system. It will be there. So basically what? This is nitrogen. Now C double bond O R, and this is plus. And now if we have another alcohol, it was acid chloride, we have another alcohol, then it is going to couple with that. Sorry, pyridine plus this ester. If we as is I am taking it R2, let's say it's R1, R1, C double bond O, O. That's why pyridine acts as nucleophilic catalysis. Third thing, pyridine is very bad electrophile. Bad electrophile. Why bad electrophile? Basically, electrophiles, not bad electrophiles, I'm wrong. Pyridine is bad at electrophilic substitution. Is bad at electrophile. There be because of some slip of the pen. I told that thing. As pyridine is very bad at electrophilic. Why electrophilic? We can rationalize it by two terms. So pyridines basically electrophilic means one electrophile that can easily take away these pi electrons. That's electrophilic. That's why if these electrophiles can easily take out the pi electron, it will be good electrophile. But pyridine, here the one cis bond is as if doped or mutated by one nitrogen. So nitrogen is electronegative. So it tightly bound out the electrons. It tightly bound the electrons or bind the electrons. That's why it's not so easily available. One thing we can explain in that way, because of as the nitrogen is electronegative, this electron cloud is quite tightly held up or bound. As the nitrogen is electronegative, pi electrons are quite tightly bound. Bound. That's the electrophile cannot take out the electrons so easily. That's a bad electrophile. Another thing, let us explain these things. Yeah. Let's say uh, electrophilic reaction, if they undergo a reaction with electrophile, then what will happen? They will generate after that generations of positive charge in ring. Now that positive charge, if there is a positive charge, let's say one is here, so it will be positive charge. That positive charge is delocalized over this. So one time it will come over nitrogen atom. That's do not like that. Basically, the intermediate will be highly unstable. That's why it is very bad electrophile. So what is the proof for that? In benzene, what happened? If we treat it with nitric acid, we'll get nitrobenzene. Now think about, we have pyridine, same thing, HNO3. Then we could expect these things, but now I learned, understand pyridine is very bad at electrophilic substitution. So this reaction will not go. Now think about another reactions. So let us, we have treated with a mixed acid. We have just used more stronger conditions. HAO3 concentrated plus concentrated H2SO4. Then what will happen? You know, this lone pair will be protonated, this plus. So we have this plus. As a result, this become again more electron deficient. This become again less reactive. Basically, stable pyridinium salt and the unreactive. That's why in that case also we have now no reaction. No reactions. It proves that the pyridine is very bad at electrophile. Let's try something different. Let's say we have taken pyridine, we are trying with for Fidel Crafts for acylations, RCOCl and AlCl3. Then what will happen? It will make a complex with this, and it will be RCl3 minus. This is nitrogen, AlCl3. Let's say this is minus, and this is plus. As a result, again this is going to be electron deficient. Then we will expect no reactions. Then how to react, we'll see it later. But what we understand, PD is very bad towards electrophilic substitutions. Okay. Then now another statement, nucleophilic substitution is very easy with pyridine. Nucleophilic substitution is very easy with pyridine. Why? I put the quotation here because it's a statement from the book of Jonathan Clayden. Research chapter is fantastically written there. Why? Let's see. As these positions, the two position of pyridine, this position closer to nitrogen, it is electronegative atom. So this position is quite strong towards strong tendency towards nucleophile. So if Cl is there, means if you also think about this way, if this kind of charge delocalizations is takes place, it do not takes place in that way, but if there is some contribution, then one positive charge is going to be there. So one of because of electronegativity, some delta plus is here. Another thing because of some mesomerizations, and mesomeric effect also one positive charge is there. That is two position. This position is very much good for nucleophilic attack. Nucleophilic attack. So let's try with nucleophile. This is Cl. If NU attack here, what will happen? These things in nucleophile Cl. This is minus, yeah, these things. Then what will happen? When it will come back, this Cl will go. That is, nucleophile will be installed at these positions. So what may be the application? So this is a one good reaction that can be done with that. We have 2-chloropyridine. Again, I am very excited to teach all this reaction because all this kind of reaction has been done by my own hand during the research. So I know how beautiful this reaction is in terms of theoretical, in terms of practical sense, all these things. If we use R2NH, then we know that. So this is very good for nucleophilic attack, and we have one nucleophile. It will attack here, and we will have these things, NR2. Definitely there is a minus H plus. Similarly, if we have these things, 4-chloropyridine, and if we treat this by RH, we know thiol is a very good nucleophile because the sulfur is highly polarized. Then what will happen? This Cl group is going to replace by SH. So what we have learned, if it was asked which statement is true about the pyridine, it is very bad towards nucleophilic, towards electrophilic substitution, and good for electrophilic nucleophilic substitution. Bad at electrophilic substitution. If it is bad for one thing, yet it have to be good for one thing. So electrophilic nucleophilic they go in quite opposite manner. That's why it is very good at. It's not always true. Just for one can visualize, and I'm telling, it's good for nucleophilic substitutions. Nucleophilic substitution. Okay. Now let us enjoy one fantastic thing. Let's say we have phenol. So if I ask you, so can you replace this hydrogen by methyl group? Okay, it's easily, because if we use a base, this base is going to take out this proton, it will be negative, and this if we use this methyl iodide, then we are going to get O-methylated product. Then if you try for same reaction on pyridine, we have OH group here, Let's try with base methyl iodide. Then what will happen? Here, you will tell the answer. Not you don't have the option to tell, but you will realize the answer in your own mind when I will show the what exact phenomenon is going to happen here. Let's think for phenol. This is aromatic one. Aromatic. If is try to go with some different form, let's say this is the form. It's a Kuhn kind of form. This is unstable, non-aromatic, non-aromatic. So phenol cannot go to this form. It will always exist in this form. So that's why as this is OH, phenolic OH, it will be replaced by OH will be replaced by methyl group. But what happened for pyridine OH? If in pyridine this kind of things happen, then what we are going to get? This is going to be double bond O NH. Yes. Then you will ask, sir, is it stable? Is this form stable? Because see here, if we have this kind of delocalization, also these forms can't come here. This is now N plus H. This is O1. Look, through this form, it again become aromatic. Aromatic. Through this form. And significant amount of this kind of keto product has been contributed to this uh, hydroxypyridine form. Significant amount of this part has been found because we'll have strong absorption band. We have learned from wire strong absorption band around these things we observe. That's mean for phenol we always have this structure, but for pyridine this structure will going to convert to some extent of this carbonyl structure and then ultimately going to another forms. So basically when let's say this is the OH group, when base is coming to abstract this OH group, this structure is going to puzzle the base. When base is approaching pyridine, the base is seeing this moiety. So no more option to abstract this base. The base is going to puzzle by this kind of structure because it has significant contribution, because this form can be again aromatic through this kind of things. It can be again aromatic. So this intermediate has significant contributions. That's why through this strategy we cannot get OME product. Methyl iodide base, we cannot get OME product. This is wrong. We have to find out some different strategy. Okay. Let us think. So what will happen on this form? We know that pyridine have significant this form. If you try with POCl3, then why this reaction takes place through this oxygenate? This is very simple thing, you know about that. Oxygen is a good friend of phosphorus. It has a good tendency to add phosphorus. And one Cl with guaiac. So basically, we have this structure NH plus, we have P, sorry, we have O, here we have P, let's think this is double bond O, and we have two Cl is here. This is the structure. Now, look at these things. We know that this place is very good for nucleophilic substitutions. Very good for nucleophilic substitution. And we have Cl minus in the systems. So Cl will come here and basically what? Just in short, I am writing this is a good living group also because phosphorus don't want that he share oxygen with some other guy. So it is a good living group. Good living group. Fantastic chemistry. So we will have this product NaCl. You can say plus, then minus H plus. We will have NCl. Basically, what? If we just in short we want to write this. If we have this kind of structure, and if we treat that with POCl3, the chlorination at two positions is going to happen on pyridine. Similarly, if you take this different structure, if the questions comes is like that, we have NH here, double bond O, and POCl3. No need to confuse that. Basically, it's a problem that has been taken from pyridine. It's pyridine. We cannot identify them because of the structure. It also pyridine. We will simply where the C double bond is present, Cl will go there. This is NH, and we'll have Cl. Okay. Then what we learned that pyridine is very bad at electrophilic substitutions because the electron cloud is tightly bound by nitrogen, you can say. Then how to carry out the electrophilic substitution on pyridine? One thing we can do, if we put or install here one electron donating group, then that group through plus R effect will increase the electron density on ring. As a result, ring will be electron rich, and the reaction will go ahead. Now let's see the example. This is pyridine. Here we have MeO, E plus, then we will have double bond OMe plus E hydrogen, ultimately minus H plus, and more step it will be E OMe. Here OMe is activating. Then see these examples. NH2, then treat with mixed acid. We are going to get here MeO, this is NH2, and this is NO2. Because of this activating group, the nitration happened. Okay. Then, for chemistry purpose, we need to do a lot of different type of chemistry on pyridine. And we know that the pyridine is very bad electrophiles. Then we need to solve the problem. If we think that pyridine is very bad electrophiles, or okay, leave the reaction, we don't want any electrophilic substitution on pyridine, we cannot do that. We have to solve it, or we have to address the problem. Then how can we address the problem? So that's the strategy. So here in these positions, we will add one electron rich moiety. Electron rich moiety. Which type of electron rich moiety? That can directly contribute its electron towards the ring. Okay, that can increase the ring electron density. And after the reaction, so we perform the reaction because the ring has enough electrons, we perform the reaction, then we will remove that group. Then remove that group. Look, in the previous case, we wanted one nitration. For the nitration, we have to install an OMe group. At the end, we cannot remove that OMe group from here. It was there, we cannot remove. That's the problem. When you are wanting or we want nitrogen, we have to install that. But we don't know, we don't want that. We'll use something here. For that the electrophilic reaction will go, then we'll remove as our need. What is that thing? That is nothing, the N oxides. Again, it is very much fascinating for me because of using N oxide in lab. See, high electron dense oxygen. The electron can directly contribute to ring by this kind of delocalizations. And as N oxide is electron rich, then with this moiety we'll have electrophilic substitution. After that we will remove that. Okay, what N oxide do by pushing the electrons to the ring by plus R effect, we have a pi electrons, pi clouds here. If we push the pi cloud by electron, what will happen? Let's say it's a homo, it's the energy levels, it's a homo electrons of pi systems. This electron is going to taken away by E plus. Very simple logic. So if you push this electron by some another electron cloud, let's say electron cloud, and we are pushing this, then what will happen? Its energy will increases. So just let us write clearly, it's a homo. Now upon electron pushing, this homo will reach here. Means the reactivity will increase. So in terms of molecular orbital also we can think about that. Okay. Another thing is that this is profit 1. This is profit 1, that as our need we have increased the electron density, we have increased the energy of homo. That is, so electrophile is going to take away the electron from high energy homo, reaction is going. Number 2 property is that N oxide is such a group, profit 2, it can be removed easily. This is enhanced electron density. And what's the number 3 profit? Number 3 property is that we know that this place of pyridine is nucleophilic. From this lone pair, it can catch a lot of positively charged. Is electrophilic. It can take the H plus or something. But by N oxide formations, we are blocking that possibilities. These 3 facilities are getting from N oxides. That's why in the first slide I told that, believe me, the heterocyclic chemistry is as beautiful as the second picture. Okay, then let us perform a reaction from this. We have pyridine, treat it with paracid, then we will have these things, minus N oxides. Now do the nitration reactions, to plus. So nitration happen. I am not showing the mechanism now. Plus, then previous classes, I told that phosphorus PCl3 can take away the oxygen from pyridine in oxide. Then we have a nitro product. See, initially we have faced the problem that you cannot do nitration on pyridine as it is not that much electron rich that nitro can take out the electron from pyridine. Is that much electron rich. Nitro have some difficulties to taking out from pyridine because the electron cloud is bound by the nitrogen. But that's the beauty of chemistry. Now we are easily converting the pyridine into nitropyridine. That's we installed one moiety that has increased electron density. Now nitro can react. Now we are removing this moiety. Okay. Now let's see. So this is COOH. Treat it with H2O2. Treat it with H2O2. So we have this in oxides. Now PCl3. If we use PCl3, then one Cl will come here, and we are supposed to write another fantasy. We are going supposed to write this in oxide, but we know that PCl3 can remove this. It's like killing a two bird by one with one, what should I say, with one kind of just one at one atom is that kind of things. Basically, already it chlorinated, install chlorine here and remove the O minus also. That's why we are not going to write anything here. Yeah, and this will be here acid. Okay, then you can ask how the mechanism happens. Let's try with that. How PCl5, because yesterday class we discussed about that. Today we have got this opportunity. PCl3 Cl, oxygen, phosphorus, Cl bonds will go. As oxygen find phosphorus, it will just bind. Now we have these things, Cl, Cl, and Cl minus. H, and we know that this Cl minus, this position is very good towards nucleophilic substitutions, and then it will leave. Basically, what happens? Just okay. I should not do step jump here. That's why no one more step because then the confusion may arise. Now the system is like that. HCl, we have these things. Cl, Cl. Now this H and this will go. Another thing we learn. So this is Cl, this is CH plus POCl2. Okay. We see some different kind of chemistry by pyridine, different role of pyridines. Sometimes pyridines can act like pyridine can replace the work of Lewis acid catalysis. So if you want to dominate benzene, let's say, then what we have to do? BF2, some Lewis acid. Here I am not discussing. There's a beautiful story. Why should I go for Lewis acid? Why bovine cannot Bromine the benzenes, we have bromine. See, so what happens? If we add catalytic amount of pyridine to the system, and it has some lone pair, we know that can catch these kind of things. Here the lone pairs populates on the sigma star of C double bonds, Br bonds, and it cleaves. So what we are getting? Br plus plus we have Br minus. Now we have benzene here. What benzene will do? It will attack here and it will go. Then we are going to get this is for example Br H, and after minus H plus it will be Br. Here also, so we are getting back pyridine. Is also another case of nucleophilic catalysis. Here, two beautiful things already happened. Let us identify them. One thing, why here pyridine acts as nuclear catalyst? Because of two things. Number one thing is that pyridine is more nucleophile than benzene because of its lone pair. That's why first reaction took place on bromine. Pyridine is more nucleophilic than benzene. Why? Because of lone pair on nitrogen. Second fantastic thing, pyridine is better nucleophile than benzene. More nucleophile and better leaving group. That's why it lives here. If it was not better nucleophile, sorry, better leaving group, then after just reaction with beer, it would not go away. As this is better leaving group, that's why it's go away. So number one, good nucleophile than benzene, and better nucleophile than, again I'm sorry, better leaving group than benzene, than bromine. I should not say. Let us clarify one thing again. So it is good nucleophile than benzene, that's why reaction takes place, and better leaving group than bromine, that's why it leaves. We know beer is also leaving group, that's why it happens. As it is better leaving group than beer, it will leave and beer will be a part of these benzenes. And pyridine, because of two things, two fantastic phenomena already happened there. So we have to isolate them, the phenomena, and we have to analyze this. First one, this, and second one is better living group than benzenes. Because of these two fantastic things, it acts as nucleophilic catalysis. Okay. In short, I'll discuss as two or three examples with the rest of the things. So this is pyrrole, NH. And what statement is that? Pyrrole is a very good nucleophile. Good nucleophile. Why? Look, this nitrogen be a part of this delocalization. So we have 6 pi electrons over 5 atom. Benzene 6 pi electrons over 6 carbon. Pyridine 6 pi electron over 6 atom, 5 carbon, 1 nitrogen. 4 carbon, 1 nitrogen, 6 carbon. Same electron clouds are distributed over 5 atoms. That's why this is quite electron rich system. As this is electron rich, it is very good towards nucleophile. Let's give a proof. We cannot do normal reaction on pyridine, electrophilic reaction on pyridine. Means we cannot do nitration. That much unreactive that thing. But here, if we allow to react with bromine at a low temperature, like 0 degree centigrade, all four position bromination happens. That much reactive. Then, if you do one reaction with pyrrole, then if already I discussed this many times, again one more times, our NME2, and so we have Hillsmer-Hack reaction with POCl3, sodium carbonate, and water. This will have double bond R. Also, we can do manic reaction over here, that different heterocyclic reactions. At the very first year, I told about these examples again, just for reminder. Me2NH, and we will have a CH2 double bond O, and we need one quite acid. That's why SUH. We will have these things. Now we have this is done by methyl substituted NME2. So Hillsmer-Hack reactions, manic reactions also happen. Now I will end the thing just upon discussing one thing. So in pyrrole, the attack can happen. This is pyrrole. This is 2 positions. This is 3 position. Attack can happen on, reaction can happen on 2 positions as well as 3 positions. But the reaction at 2 positions is quite better. 2 positions quite better than 3 positions. Why? Let us explain that. Now we do the reaction by 2 positions. NH, this, and this is the electrophile. Then what is the intermediate? NH plus, this one, H and E. Look the intermediate for 2 positions. After that, minus H plus, it will form this. If the reaction happen on 3 positions, then what is going to be? Pyrrole this is the reaction at 3 positions. Then what we have? We have these things. NH plus EH. After minus H plus, we will have NH E. Now we'll take out this intermediate and compare with this intermediate. N plus, this is the intermediate H. What is the difference? This intermediate, there is very small difference. These two almost look similar. The one small difference is that this is more stable, and this is less stable. You will ask why. If I normally ask you why this is more stable, less stable, it will take a lot of time to think about that because the proximity is very much similar. Okay, look, once it will come here, just it will A. This pi electron come here, and these pi bonds with or pi electron lie on nitrogen. Means it is linearly conjugate. Linearly conjugate. Conjugate. And here, look, this pi electrons is not associated with these pi electrons. Okay, like here, double bond, single bond, double bond, here is the plus. Double bond, single bond, plus, again double bond. So the conjugation is cross conjugation. Cross conjugation. Here, linearly conjugations. That's why this is quite stable. Here, cross conjugation, double bond, single bond, plus. Look, from this direction, this double plus double bond is not related to this one. That's why cross conjugation. That's why if which is true or false, this kind of statement is given that attack at two positions or reaction in two positions, reaction in two position is quite better favorable than three positions.